Okay, so I think there are still some students on their way, so let's wait for maybe 3 more minutes. And in the meanwhile, if you have any question, please feel free to ask. Okay. For the final project and the last written assignment, they will both be due next Monday because today is the last class. We are talking about dimensionality reduction. Okay. And so the assignment, for the written assignment, you should already be able to do, I think, a question 1, 2, and 4. For question 3, you should be able to do that when we finish this class. Okay. And so for the final project, I think some students already tried that. We also tested that you will definitely work with TensorFlow 1. Okay, for TensorFlow 2, there may be some compatibility issues, so you may want to downgrade your environment to TensorFlow 1, to do with, mask Gaussian, but it's not required that you have to use that mask Gaussian we provided. Okay, that's just the one that we tested, and be sure it will work. Okay, so there are also, PyTorch version of mask Gaussian. There's also YOLO. You can use whichever version you like. Okay, so you can also choose to do the segmentation, or you just do the, object detection. You don't need the mask, only bounding box. That's also fine. And yeah, so one student asked me whether I can extend the final project deadline. So here's our recommendation, okay, because the last week we have to finish all the markings. And so we can extend a little bit if you cannot finish by Monday, right? So one thing you need to pay attention, for PhD students next Monday, you need to give a presentation of the final project you did, okay? So that's part of the marking scheme. 20% will be on the presentation if your group has a PhD student, okay? If not, you just need to submit, right? So submit no later by, midnight Wednesday, okay? So after that, we probably don't have enough time to mark your assignment, right? So you think about it, because, the Monday afterwards, we need to finalize all scores and upload, okay? So if you don't give us like at least 3 or 4 days, right? Because we have so many students, okay? So yeah, so no last moment submission. Okay, if you extend it for 1 or 2 days, that's fine. Okay, for the written assignments though, you have to submit on time because we are marking both assignments in parallel. So both TAs and I will be busy during the last week. Okay, the next week.
Professor, you also expect a report as well by 7th?
Yeah, so all PhD students will need to give a presentation of their projects. Okay, not all PhD students, any group with a PhD student. That
like
group,
a written report, sir. Like
what report?
Like other than the presentation, we also have to submit a report, right?
Exactly. So the report can be relatively simple, just what you did in the project and what are the programs how you run it. But again, you can submit along with because if you use a Jupyter notebook, the notebook itself can write some notes, right? So you can put it in the Jupyter notebook file. Okay, that's a lot.
So the report doesn't necessarily have to be a PDF. It can be directly done in the notebook.
Yeah, you need to have this description. You cannot just throw a bunch of code to the TA and me, right? So we need to have some,
Yes,
we understand the overview, what are doing, what are you doing for each step, what's the purpose, and finally what's the result you get, right? So like you can demo a few of the test images, right? So you cannot just throw a bunch of code, right? So then we will have to maybe contact you again to figure out what you are doing. Right.
I see. Thank you so much.
You're welcome. So the main purpose for the report or any note is to help us understand what you did. Okay, so this is very important. And yeah. And again, I want to re-emphasize, we tested this project. It will run through if you use mask Gaussian, but we only tested on TensorFlow 1.0. Okay, maybe 1.4 or 1.14 or something. Okay, we didn't test the training on the TensorFlow 2. So the safest choice is to use our online code to split the training images that we have shared the link, and then after splitting, run mask Gaussian on the split files, okay, and see whether you can detect those objects. Right, this is the safest path, right? And you follow the there's the mask machine learning mastery, right? So actually, annotation file in YOLO format. I see a question. Yeah, both are fine. Okay, you can use any format to. So it's basically, the annotation file that we provided is in VIA format, right? So you need to convert. If you look at our code, we are also just doing a JSON parsing and get what you need, right? If you want to use the YOLO format or any format, I don't see the point, because you need the format to be imported into your model to train, right? So the format is not that important once you get into the memory and throw it into a machine, whether it's YOLO or Mascasian, right? The important thing is you get the annotations. Our annotations is in VIA format, okay, not in YOLO format, right? So you need to write another code to pass the VIA format into a in-memory structure that, let's say, YOLO can understand and can import, okay? No matter what format it is, I think after loading, there's a data structure. That's what you need, okay? And we have the demo code on how to pass those information and put them into the main memory, right? So the Python objects, okay, in a split code. You just read that split code, which we already passed via, okay? And reading JSON code is also very important, right? So JSON is basically, JavaScript, I forgot the name, JavaScript object format or something, right? Yeah, so
JavaScript object notation, sir.
Yeah, basically, originally it was for, JavaScript, right? So for the web, visualization, moving the web constructs objects, okay? And because in JavaScript, everything object is a dictionary, okay? So it's just that you have a field, it's field is just the name of the variable, and the value is, the dictionary value. The key is a variable, okay, for that object, right? So then if you look at Python and JavaScript, the semantics is basically the same. You have the array, which is the list, you have the object, which is the dictionary, okay? So it's very easy to directly, it's compatible in some sense, right? So it's just any middle format, just like CSV. Okay, so I don't think if you care about the YOLO format or particular format, right? So you care about how to get this format into your memory and throw to YOLO model, okay? If you are in YOLO format, it's okay, but our data provided is not in YOLO format, right? So you need to check our splitting code, how we pass the data, okay, and then throw to the right data structure in memory so that YOLO can take it. Right, so that's basically it. Usually in deep learning, you will have the X-train, Y-train, something like that, right? So what you need to do is really see what's the X-train format, right? So, and you need to format it properly and throw to them. Usually you have the bounding box, right? You have the class, right? Which usually is in maybe the target in Y, okay, X is usually the pixels, right? So the images, okay? So I think I answered the question, right? So yeah, so if you use your own data set, you need to justify why you want to use it, right? So maybe because you want to skip your own part of loading the JSON file, right? So you don't even want to write the parsing code, right? So you want to copy some existing library online code and directly import their data, which is already there. You don't even need to work on the data loading part, right? So if that's the case, you need to justify why the data is equally difficult as our data, okay? And we will deduct the mark that you skip for the parsing of the data, okay? Because you are just copying other people's data, loading part, okay? Because we already provide the JSON parsing code in our image splitting GitHub link, right? So if you read Python, you read the code, you should be able to work it out, right? So that's basically it. And we will be fair, basically. If you work on some simple project, you need to give them approval. And unfortunately, we will have to deduct some mark because other students are working on it already and get good progress and asking questions to me, right? So if you work on it at the last moment, we need to be fair, right? So, okay, so again, so if you finally you cannot make it work, do contact me, okay? We will allow you to do some simple project. And the purpose of using our data set is because, it's like a processing, right? All your students have collected data set, and so that we work out this data set, right? And then it's a unique data set. You cannot copy from the web. You cannot reuse for another course project, right? So that's a purpose, and it's required by the department, okay? And don't worry too much about the grade right now. We will see how students perform. If it's too not too good, we will curve the grade a little bit. Okay, but we will decide that in the last moment, depending on how many students get A, how many get B or C, right? One thing that we cannot change is, the department recommended that this semester above 90 is A. Okay, that we cannot change, right? So if you students were taking my course previously, you should know that we are much easier, right? So the final project of your own choice, and if you are above 85, you are A, right? So, but this time at the beginning of the semester, the department explicitly have the rules like 90 is A, okay, below 90 is B, right? So we will curve if necessary, but after curve, we will follow the marking scheme, okay? And if you cannot work it out at the last moment, at least make sure you have enough time to work out another project. We will deduct the, the fairness mark because you are working on a simple project, right? So we don't want to let you totally lose all the scores, right? So, but you need to let me know, okay? And approve it, okay? And we will have to deduct some points, okay? So that's it. And again, the recommendation is read our GitHub link for image splitting for the parsing code, okay? And you can go with machinery mastery, you can go with any YOLO online tutorials, right? So keep in mind the purpose of the project not let you move around the deep learning internals, right? You know the loss, okay? The loss is like a classification for what is in the image, regression for where the box is, and finally, if you want, you can work on the segmentation, which is like each pixel, whether it's this object or not, right? Binary classification, okay? And it's called segmentation, which is pixel-wise classification, right? All these supervisor concepts, you can take a look and you have experience on that more complicated project beyond what scikit-learn that you already did in a prior assignment, right? Okay. Again, I want to emphasize that you start work early, and if it doesn't work, if you are going with Matterport's Mascasian, downgrade your TensorFlow to TensorFlow 1 instead of TensorFlow 2, okay? And start early. And if truly you cannot work out last moment, you can contact me, okay? So we will see whether with some deduction of the difficulty marks, you can work on other projects, okay? But you want to try this project. We tested it, it's not so difficult. If you follow these steps, you can make it run, okay? And some students may think that the data set is too big, right? So we have maybe 4 GB data, and after decompress, etc. And if you even pass, so the solution is that you don't have to work with the entire data set, okay? If you have enough disk space, let's say you are working with Chiha, it's easily handled, right? So, but if you are not, you are working with your own environment, right? So then you can downscale the data, right? Use only 10% of the data, for example. Okay, the important thing is demonstrate you are able to train the model and the test, and you can detect some objects. It may not be very high quality, but at least you can make it work in some way. Okay. So that's yeah. So that's for the final project, and today we will be our last class. Okay, so we will talk about dimensionality reduction. Okay. And this semester we have been a little bit slow in the progress, so we skipped some chapter, but I think this one is the most important. So in the last class, I want to cover the dimensionality reduction only. Okay, and yeah, let's begin. So just want to make sure everyone can see my screen, right? Can anyone let me know if you are okay to see my screen?
Yes, we
Yes,
can
we see
see.
the slide.
Okay, thank you. Yeah. So why dimensionality reduction? So it usually happens that in your table, right? If you only have like 10 or 20 columns, you really don't want to do dimensionality reduction, right? Because we are with UAB, a lot of the departments, the schools are medical related. If you look at the health records, right? So it's really high dimensional data. Sometimes even time series, right? So like EEG, some, and a lot of like different kind of tests and heart rate, etc. Okay, usually the dimension can go to hundreds, right? Often go beyond 1,000. Okay, if that is the case, that's when you really want to do a dimensionality reduction. Okay, let's say you have more than 100 dimensions. Okay, and it's recommended. I would say that for TensorFlow, not TensorFlow, for scikit-learn, those libraries, if you have more than 100 attributes, you do really want to do dimensional reduction. Okay, those models are slow when the dimension is high. Okay. And so dimension reduction, there are some benefits. Firstly, is the time and space complexity, right? So if you reduce your data originally maybe 200 dimensions, now you reduce to maybe 5 or 10 dimensions, let's say 10 dimensions, right? And that's a huge save when you, in the second stage, you take your dimensionality reduced data into a support vector machine, decision tree, or neural networks. Okay, that's way faster. So another important thing is that the model is simpler, right? And then it will be more robust. Oftentimes, if PCA, which we will cover later. Okay, so if you do a PCA, which is eigen decomposition, usually you will have so-called principal components, right? The most important component, a secondary component, which are big values. Okay, and later most of the part will be very close to zero. These are noise, right? As we said, when you collect your data, you may have measurements error and human error, and sometimes other kind of noise, right? So the regression itself will have some noise from the background. Okay, right? For those kind of problems, right? So actually, they should not be part of your data. If you recall what we have earlier, right? So we talked about a sine function where we fit with a polynomial function, right? Because sine function is perturbed with some noise, right? And if you get rid of those small components, these components are more like noise, because they are get rid of. And that's why sometimes after dimension reduction, right? You think you actually compress the data, the information is loose, but actually your model is more robust and your test accuracy is higher. Okay, so don't be confused even if you find, hey, I do a PCA and my model performs better. Okay, this is often the case actually. And simpler models are often more interpretable, right? So, but this actually later you will see if we do feature extraction, the features themselves are not interpreted anyway because it's transformed over the original features. Okay, but if you do so-called feature selection, the features are original features, right? So then if you select those main components, it's still explainable, right? So if you then train with a decision tree, right? So then it's actually very explainable. So it depends. Okay. Another important application is called data visualization, right? So if you have 100-dimensional data, you cannot see what's happening with the data. Okay. What you really want to do is with two or three dimensions. Okay. Right. So 2-dimensional you can plot, right? So 3-dimensional you can also have a plot which is 3-dimensional plot, right? So you can usually drag the cameras and rotate and see what's happening there, right? Unfortunately, we cannot plot beyond 3 dimensions because we're human. Okay, right. So if you plot and you do a visualization, right, like a PCA, and sometimes these days there's another algorithm I'm not sure whether you heard of. It's called a Tisney, right? So it's a nonlinear. Will not be covered in this lecture. Okay, right. So this is another data visualization tool. Okay, it's nonlinear. All we cover is linear transformations. Okay, linear methods. Okay. And then you will see the data cluster, right? So if there are 3 major clusters, you will be able to see that after, dimensional reduction. Okay, because dimensional reduction really captures the major information and throw out those noise or throw out those less important dimensions. Okay. So there are, as we said, there are 2 different methods for reduced dimension. The first is called feature selection. The second is called feature extraction. What's the difference? So feature selection really, you have already have maybe 20 features, right? You only want the 5 most informative features. These 5 features are among the 20 features, okay? So you know their physical meanings, right? So this is what we usually do, right? So you originally have d-dimensional features, okay? You only want your model to work with k features, right? So what you do is you select a subset of features from it, okay? K features, right? Which is much smaller, but also captures most of the information. And then you build your machine learning model using just the K features. So this is called feature selection. Another method is called feature extraction, right? So the feature extraction basically will again, you will specify a k, right? How many dimensions you want to reduce to. And then we will do a transformation. Okay, it's usually a transformation that changes the meaning of those features totally. Okay, so there's no longer any physical meaning. It's a linear transformation of the original feature vector. Okay, but then you have those major principal components, right? And you can throw out the noise components. Okay, and that actually gives you best performance when you use these, like say PCAs, those kind of feature extraction to do machine learning. Okay. And so this is feature extraction really for the effectiveness of your target problem, right? So supervised learning, okay? And feature selection is for interpretability. Usually you do feature selection and then train with the decision tree, and then you can see how the decision tree works with each attribute, right? Less than, like age less than some, you go to this branch, age larger than that, you go to that branch, okay? But the feature extraction really, you don't need any interpretability. I just don't want to, hey, give me X through this feature extraction, and then your machine learning model F and Y is actually much better than if you just use simple selection and decision tree. Okay, so that's the purpose. So feature extraction, there are also two kinds of methods. One is called the unsupervised method, which means that you just look at X, you don't look at Y. You want to capture what's hitting the data, which are the main components. Okay. Another method, so we will see all three methods this time. Okay, PCA, factor analysis, and MDS. Okay. So PCA is the most common one where you have coordinates. If A actually is a generalization of PCA. Okay, PCA is a simplified case of FA. And MDS is when, let's say, your data points do not have coordinates, or you don't know the coordinates, right? It's, let's say, if you have a graph structure, right, in a social network, right, you send messages to each other. In that case, it's more suitable for using MDS. You know the distance, right? You are 3 hops away from that point, that person, that you know, okay? But you know the pairwise distance. You don't know what their coordinates are, right? Because in the topologic space, there's no coordinates anyway, right? So then you want to use MDS to reduce the dimension. And there's also a supervised method, right? So, if you know that your feature extraction function is serving that particular task of predicting Y, why not giving also Y to your data, right? And then when you do feature extraction, you extract those features that's the most suitable for your prediction of Y, okay? So we also have a supervised method called linear discriminant analysis, right? So this method is actually, having the same name as the latent direction allocation for topic modeling, but don't be confused. LDA for here is dimensional reduction, but you have Y, you have the supervision, okay? So the linear method above also have nonlinear extensions, right? So, but we will not cover them, right? So here you will see that all our models are doing a linear transformation, okay? So first, let's look at feature selection. This is actually very simple. So the goal is find the best set of features that can capture the whole data, okay? And the best set of features should, have the least number of dimensions, but contribute most to the accuracy, right? So if your data is really X, Y, Z, right? So the other features may be redundant. Maybe some are X squares, X cubic, you want to throw them, okay? Or almost the same as X, right? So with very small difference, okay? They are not, it's kind of redundant, right? So again, for feature selection method, usually there are two different methods, right? So one is you can give a K, but when we describe this method, basically the algorithms themselves will select a K for you, okay? You just give, let's say, 100 dimension, and they say, hey, give me a bunch of features that are best, okay? You don't even need to say, hey, give me 10 features that are best, right? And unfortunately, this is a NP hard problem, right? So you can think about it. Each feature you have, whether you take it or not, right? So if you have 100 features, that's 2 by 2 by 2 by 2, 2 to the power of 100. This is impossible if you try all the subsets on your models to train it, right? And to see how the accuracy looks like on your validation set. This is unacceptable, right? And here we -1 because, there's an empty set, right? You will never choose, right? So always choose some features at least, okay? So exhaustive search is impossible, as we said, unless D is really small, maybe 3 or 5, you can try, okay? 2 to the power 5 is just 32, right? So it's okay. And heuristic algorithms are often needed, right? So because you have a very high dimensional space, that's why you are doing dimensional reduction, Okay, so they may be suboptimal, but they make sense, right? The trend is okay. So you are not optimal, but you are not far away. They make sense. The method makes sense. The result is not too bad. Okay, and they can finish in reasonable time. And there are two methods. The first is called forward search. The second is called backward search. Okay, so the forward search method basically says I start with an empty set, right? So and then each time I select a feature that is most descriptive, and I add to the current set. And next time for the rest of the features, I continue to select. Okay, and backward is like I start from the entire set of features, right? And each time I kick out some features, right? So kick out one feature, and the next time for the rest, I kick out another feature that's the least informative. Okay. So here are the typical method. So if you look at scikit-learn, there's a method called RFE, I think, right? So recursive feature elimination, okay, RFE, okay? So that's doing backward search. I think there is some parameter, like say each time you kick out each iteration, you may not just kick out one feature, right? Maybe that's too slow because backward search, as we will explain, will be much more expensive than forward search. Okay, maybe each time you kick out 10% of the features, etc., right? So that the algorithm can run much faster. You can check, scikit-learn documentation, RFE, okay, recursive feature elimination. And recently, people find that if you apply a regularization, if you remember, we have L2 regularization, L1 regularization, right? So if you have an L1 regularization, then you will induce sparsity. This is like our support vector machine. If you remember, we have alpha, but most of alpha will be 0, right? So this kind of thing can be achieved if you apply a L1 norm also, okay? The L2 norm is more like a Gaussian regularizer, right? So L1 norm is, if you know it, it's, I think it's a Laplace distribution, right? So it has some trend to make most of the features, the coefficient to be 0, okay? If you are doing a linear transformation, okay? So only a few features matters. And then, so for those coefficients that are not 0, you take those features, okay? So that's another method. So L1 norm sparsity inducing methods has been hard for quite a while. But again, the backward search, the RFE in scikit-learn is probably some first thing you can try out. And here, the forward search, what we do is we start with no features, right? Empty set. And each time we add a feature, okay? That's the most informative. And of course, you add a feature, it's the most informative feature. It should decrease error when you train and test on your test data, right? If the error no longer decreases or even increases, like a backfire, you should stop. That's where you say, hey, now I tried this as these 7 features. When I select the 8th feature, I cannot select the 8th feature. That further reduce my error, right? In that case, you just take those 7 features as your final feature, okay? That's actually possible. Intuitively, you can think that the other features are kind of redundant and also have some noise introduced, right? So during the measurements, okay? In that case, those features can be totally kicked out. Okay? So actually, this is not exactly true because we are doing feature extraction selection, right? So feature extraction will be able to utilize the other features information, right? There's some feature information that's orthogonal to your current 7 features, right? But they cannot be utilized if you use feature selection, okay? The benefit is that you are using original attributes, right? So they are meaningful, okay? So the error can, for classification, if your machine model classifier, then it's misclassification error, right? So 1 minus accuracy. If you are doing regression, you will compare the mean square error, okay? Keep in mind this is called mean squared error. Okay, some people just miss a D. Okay, it's squared error. Right? So you square your error. The error is squared. Right? And so you should be measure this on a validation set, which means, hey, now you extract those 7 attributes, right? You train on these handwritten data rows, and then when measurement errors, you should measurement on another data set, maybe hold out another 50 data, test set, or we call validation set. You should not use the original 100 rows, any of the rows, okay? Because you really care whether these 7 features will make your model generalize, predict unseen data, not on the data you see, okay? You already see them, that makes no sense unless you want to do data compression, okay? So the algorithm skeleton looks like this, right? So originally we may have an empty set, right? In each iteration, what we do is we will for each available xi, which is not already chosen into F, okay? You will train your current feature set with that feature. So basically, let's say you already, so right now it's empty, so you only have one feature. Right? You try each feature once, right? Let's assume you already have 7 features, right? Now for the remaining, let's say we have 20 features. For the remaining 13 features, right? For each of those 13 features, you will try 7 features plus that feature, right? And then you train that model and test on the validation set, and then you find this particular feature among the 13 features, remaining features, that gives you the best performance on the validation set, okay? And then you will compare the best so far with the error if you don't expand the 7 features. You just use the 7 features to train your model, right? If you find that, hey, after adding this best remaining features, my error reduces, right? And then I should add my feature to the F, and I continue to select the next feature. On the other hand, if you find, hey, my best feature still cannot reduce the error, right? Then other features definitely will increase the error, right? So you can exit. That's the F is the final F you want. Okay, if you have any question, you can ask me anytime. So what's the cost? You remember the first time if F is empty, you just try x1 to xd, right? The second time you already have one feature, so the remaining feature you try is actually d minus 1, right? Or if you have 2 features already in the set, you try d minus 2, right? If you already have k features in the set, you will try d minus k. Okay, so this is the number of features you will try, right? So this is try with, try to select the first feature. This is try to select the second feature. This is try to select the case feature. Okay, because initially this d corresponds to when you have 0 feature, f equal to empty. Okay, this is equal f equal to k. Okay, so this is because the last time keeps, you do need to try and see, hey, I'm not improving. That's where you stop. So that's so many times you train your model, right? Because for example, the first time for each of the d items you will train a model. Right, so you train d models. The second time you train d minus 1 model. But even though there's no guarantee of optimality, this is a greedy method, right? So it's still working, right? So in most of the cases. Another method is backward search, which tends to give you better results because you are more conservative, right? You don't aggressively take the most informative one. You start with all features. You think everyone should be counted. Then you kind of kick out one feature at a time, right? So this is a reverse method. F now start with all features, not an empty set, right? Then for each feature already in F, right, not kicked out, right now still in F, we will kick out that particular feature from F and train a model, right? We will do this for every remaining feature in F, okay? And then we find the best model, right, and find its feature error, okay? Let's assume xj is the best feature, kicking out xj from F gives you the best error, okay? In that case, you just compare, right? So if you kick out j, which are already reduce the error most, if it's smaller than if you don't kick out anything, right? If you remove xj, it's better, right? So you will remove F and continue then for the remaining F, you continue to remove the next iteration. So you kick out xj, it's not improving, right? Then it means you should not kick anymore. These information are important, right? You stop. So using this method, the cost is much higher. Okay, if you look at the cost, right? So initially you will have D, right? Because you kick out x1, kick out xd, right? So you have D all in F. Okay. Next time you already kick out one attribute. So in in F you only have D minus 1 that you can choose from, right? So all the way you need to kick out. You need to finally have only k attributes remaining F, right? So you will kick out, you will kick all the way to, you only have k plus 1. But then you kick out one attribute, it become k. So it compares these. This is how many models you need to train. It compares these two, right? So this is much better, actually, if you look at it, right? So usually we do dimension reduction because the dimension high. Let's say D is 100, 199, etc. All the way plus to a small number. Let's say if we really just want to kick out 10, k equal to 10. So we go from 100 to 90, okay? But on the other hand, if you are doing something here, if we go from 100, it's all go from 100 all the way to 11. Right? So this is much larger. Okay, this is more costly. So this is one thing. The second thing, you think about it, right? This D is actually meaning that you start from one attribute because F is empty initially, right? So you are training a model with only one attribute. So these D models are trained much faster than if you compare with this model. These D models, let's say you have 100 attributes. Each model is trained on 99 attributes. You kick out one attribute, right? So that, this is much slower. Okay, so backward search is more expensive, but it's what's implemented in scikit-learn. I believe there they actually kick out maybe more than one each time. So it's like a D minus a step length, maybe 10, D minus 20, etc. to make it tractable if you have very high dimensional data. Okay. You can study the documentation. I didn't use it often, so but that's some tool that you can refer to. Okay. And so yeah, as we said, usually if your K is a really small 10, your dimension is big 100, that's where you want to do dimension reduction from D to K, right? So training a model with more features are more costly, right? So the first part why backward search is more expensive because this chain is much longer than previous chain. The second is because this cost is also much larger than if you use forward search. Okay, train a model with more features in the backward case. Again, there's no guarantee of optimality, and so that's feature selection. Okay, feature selection selects those features you already have, but you don't convert to some other features that are not so intuitive to you, right? From the next few slides, we are talking about feature reduction, which is feature extraction. Okay, feature extraction means you transform those features into another space, right? So this is like a kernel method in SVM. Okay, but here it's different. Right? So it's just reduce your dimensions. Okay, but those new dimensions are not intuitive to you anymore, but they are effective when you train machine learning models. Okay, so let's look at PCA. Right, so PCA finds a limit mapping from your original D-dimensional space to K-dimensional space. Right, D is maybe 100, K is 10. We keep that in mind so that you can get something. Okay, and by doing that, you will lose information for sure. Right, so you want to minimize the information use. Okay, because if you assume that even in the D-dimensional space there's some noise, you don't know which part of noise, right? So you lose the noise, it's also information, right? Okay. And here we need to define some criteria, how to measure what is good, what is bad, right? So we will see PCA measures that using variance. Okay. So here, let's think about this thing, right? So let me have a pen, and so let me try to. Yeah, so you think about, assume your original data point, let's say this is the origin, okay? The original data point is X vector, okay? Now what we are saying that we want to map, maybe this is X1, right? This is X2, you have a bunch of points in the data space, okay? We want to map those points along a particular dimension, let's say this dimension, okay? This may be, this is this direction W, right? So when you map, for example, this guy map to here, this point. This guy map to here, this guy map to here, this guy. So this is what we are doing, right? Let me clear this a little bit because I think the previous one is not so good. Okay. Now this is our setting. Okay, keep in mind we have a bunch of X data points. Okay, now let's think about a particular direction W. Right? When we talk about direction, we are really thinking about a unit vector. Okay, which means the vector length is one. Okay, and now let's consider a data point. Let's say this is a data point. Right? So when you map to this W, what will be its coordinate Z? Right? If you think about its one-dimensional axis, right? What's this Z? So this is really X, the length of X cosine theta, right? So it's really X cosine theta. Theta is different, right? So we can also write an inner product between W and X, okay? Because this is really W times X, right, times cosine theta. And we remember W is 1, okay? So this is done. So they are the same, right? So basically, if you take inner product, it's like the coordinate along the W direction, but the W has to be a unit vector. Okay, so that's what we see. So after doing this inner product of x along a direction W, you get the coordinate on W. Right. So this is intuition. Now let's take a look at how we find a direction. Right. So here's what we want to do. You have a point here, 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 you have a point here. Right? So which direction works the best? The best direction obviously is not this direction. Right? So if you map here, you will have a small range. Okay? Right. So this is small. Right? So you lose a lot of information that is descriptive. They are almost clustered around this range, right? Along this direction. Maybe this direction is best because after you map, this is much longer. Okay? So that's split. If you lose the distance is small. Okay, compared with if you use this one, that would be distance. So what it means is that, let me clear it. What it means is that we want to choose a particular direction W. Right, so you have a bunch of points. We choose this direction W. After mapping to W, right, then what we do is we evaluate the variance on here. Right, so here may be a little bit counterintuitive. Actually, we want the variance to be maximized. Right? That means, it's spread along W. Okay, right? So if there's a cluster on W, which means it's not able to differentiate with them, right? If they are spread along them, have very different coordinates, then this is best. So which means if we map them, right? So it's x1, we map to W, Z1, Z2. Okay, here we have Z1, maybe Z2, Z3, and we want to maximize the variance of this. So what we'll do is you think about it, how to compute variance, right? So originally, in the original space, that's the center of this data points, x is here, right? And when you map to here, you have a z variance, okay? Z mean, okay? This Z mean is actually, you can easily show that this Z mean is also the mean of z, so states that you map to, okay? So this is, you can easily show. If your mean along every dimension, right? So because, the mean is computed along every dimension. Then no matter how you map it, right, so along any direction, the mapped coordinate is still the mean, right? Yeah, let me clear this. Okay, here now let's think about how we can find a W that maximizes the variance, right? So here we have this data point, right? And this now becomes a random variable. It can be any value in your data set, okay? And we map it along this direction. These are the coordinates, right? And we want to maximize the variance of the coordinates, right? So how do you compute it, right? So this is your W, right? And so here, this is your, let's say this is your X, right? So this is your coordinate, okay? This is Z, so after mapping to it. And what is this? This mu is really the center of your data set, okay? And when you map to this W1, this is your center, your mean along this direction, right? So you can easily see that here is Z, this is Z mean, right? So this is the definition of your variance along this direction. Any questions? If not, we will continue, okay? So now the rest is what you should be super familiar. Okay, so, this thing times this thing twice. It's like this, right? And, if we look at this, what is this? This is W1 transpose, X1 is mu. And you will be able to see this W1 X mu, both are what? Both are vectors, right? So it's an inner product. So, inner product, you can swap them. So this vector and inner product, this vector. Oh, no, there's no T. This is inner product, okay? If you swap them, you get this, right? And now we know what. So here we assume W1 is a direction, right? So this now for us is a constant. Right? So we are taking, remember the variance expectation taking on this random variable, which is randomly selected from our data set, right? So when they are constant, you can take them out. Then we are really taking the expectation over this part. And this part is actually the covariance of your data set, okay? So if you don't remember why, so just remember we have the outer product, right? So this outer product, okay? So the ijth item is really xi minus mu I, xj minus mu j, right? And you take expectation. Because this is a matrix, expecting a matrix is taking matrix inside each other. Okay? So this is what? This is really the covariance of xi, xj. Okay? So the entire matrix is a covariance matrix. Okay? So let's review this conclusion here. Right? So the variance of your data set along this W direction, W1 direction, can be represented as this quadratic form. Okay? This quadratic form gives you one value, okay, which is the variance value. Right? So this quadratic form is really your covariance of your data set and your direction. Okay. Now what we want to do, if you remember, we want to maximize this variance, right? We have different W1s, even though it's constant, it can take different constant values, right? So again, it's a direction, right? So it's a unit vector. And we can rotate this W1, right? So we want to maximize this variance, right? Because we wanted the data to be spread out the most after mapping to that direction, okay? So this is a constraint of optimization problem, right? So if you go back, you want to maximize this, right? But we do have a constraint that this is a unit vector. Okay, so this gives us something like this in Lagrangian form. Right. So this is the target. We want to maximize. Right. But this is a constraint. Right. So this is basically W1 transpose W1. Right. Because you can square. So the square is equal to. And then you move this one to here equal to 0, and this becomes a condition, and this is Lagrangian multiply. So we will go a little bit faster because we have 50 pages today. Okay, so if you have a question, you can stop me. Otherwise, I will go a little bit faster. And we have the video, so you can always watch it offline. And so now what you do is this, right? So this is the what? This is the Lagrangian form, right? So this is the optimization target in the dual form. And what we want to do is we take a derivative to W and also to alpha. Right? These are the newly introduced variable alpha, original W, which we want to find the best W. Okay, and then set to 0. Okay, so let's. I think by now you should pretty be familiar with how to take this derivative. Okay, after this machine learning course, at least all we require you is to remember these two forms. Right, so this is what? This is ax squared. Right? X is the W. Right? After taking derivatives, so 2ax. Okay. In this form, it's really what? It's a sigma W1 times sigma transpose. It's a ax plus a transpose. Okay. But sigma is symmetric. It's a covariance matrix. Right? So it's really two sigma. Okay. Here now you should know easily that this is 2w1. Okay. Right. So we have shown this again. Right? So this is a minus 2 alpha. This is around 2w. So equal to 0. This is derivative to w1, and we set to equal to 0. Right? So this is 2 sigma w1 equal to 2 alpha. Okay, and the 2 can be cancelled. So we get this. We get this. Right. So what is this? Unfortunately, we don't have time to go through, eigen decomposition, but this is really eigenvalue. So what it means is that if you have a matrix A, here is sigma, right? Then you do a linear transformation with some vector. But if after doing the linear transformation, you get another vector, the vector, the input vector and the output vector are along the same line. Okay, right, so you really have a vector and go through this matrix, you get another vector. Right, the direction is the same. Okay, they are the same direction. It's just that the magnitude changes. Right, then it's actually this W is discrete of this matrix. It's an eigenvector. Alpha is an eigenvalue. Okay. So let's maybe let me spend some time to give you the conclusions, because we don't have time to go through everything. So usually you will have a matrix which must be square, by the way, right? So because you have a ax equal to y, right? So x and y should be in the same space, right? So along the same direction. Of course, if this 10 dimension, this 10 dimension. So this A has no choice but to be 10 by 10. Okay, and so given a square matrix, right? So when you do eigen decomposition, it can be decomposed into something like, P diagonal P transpose. Okay. So here so if you write it like this, right? So this P is more like those kind of, we call it eigenvectors. Okay. That's called W1, W2, and D is what? D is a diagonal. Okay, that's called lambda 1, lambda 2, and PT is transpose. So this is W1 transpose, W2 transpose, because W is a column vector. Okay. So any matrix you can decompose like this. Additionally, if this matrix is a symmetric matrix, okay, it's a symmetric, this value are the same, okay, which is the case in covariance matrix, then we are guaranteed those lambdas can never be negative, okay? And those lambdas usually will go from positive, larger than equal to lambda 3 to some very close to 0, okay? It's always larger than or equal to later than. So this is for any square matrix, you can decompose. And additionally, if this matrix is a square matrix, you can have this feature. These are like this. Okay. So in order to see, so these two are equivalent actually. You can show that this also means this. Okay. So yeah, because we are not in linear algebra course, so just the conclusion we gave. Okay. For this W1, lambda 1 is alpha. Okay. Maybe W2 is a lambda 2. So for these vectors, if you time them to this matrix, you get another vector, which is along the same line. Maybe it's the reverse direction if alpha is negative. Okay, but if you are having symmetric matrix, alpha is always positive. Okay, so let's continue. So because we have this, right? So what we can easily do is we can find W1 transpose and W1 transpose on both sides. So this gives you this. But alpha is a constant, you can a scalar, you can look here, and this we know is 1, right, because of this field. So this is alpha. Okay. So what does this mean? This means that if you look at this item is exactly this item, which is our variance. Okay, our map variance. So our map variance is exactly alpha. Right? Is the alpha is what we want to maximize. Okay. So as we said, if you do eigen decomposition, you have lambda 1, lambda 2, right? So this is lambda 1. One of the largest eigenvalue. Okay. So we will choose the eigenvector with the largest eigenvalue. So W1 is the direction, its associated eigenvalue alpha will be the, that's the variance, controlling variance after mapping along W. Any questions?
So again, eigenvalue is a scalar or a vector? It's a scalar, right?
Alpha is scalar.
Yeah, okay. Yeah.
Alpha is scalar, right? So this is a quadratic form, okay? Quadratic form is scalar, which is the variance after you mapping along the W1 direction. This is the coordinates. Is okay?
Yes, sir. Thank you.
Good. All right, so the reason we want to choose the largest eigenvalue and the first eigenvector is because, this alpha is corresponding to this thing. And this thing has a physical meaning of variance. And we want to minimize the information loss, which means after mapping to Z1, up into W1 direction, the coordinates should be maximized, right? So the variance should be maximized. So we want to maximize this, which is up, right? So this should be the first eigenvector. So now let's go continue, right? So this is basically the first dimension you extracted, right? So now we also want the second dimension. So one key information that you don't want any repetition of the information. So whenever we choose a new dimension, we will have orthogonal requirement to the original dimension. Okay, let's say this W1, then W2 should be orthogonal. So if you are not orthogonal, you have some components on W1, right? So you can merge this information to W1. Then you just take this. So you will always consider orthogonal unit vector. Okay. This is like if you have a bunch of points. distribute in this direction. The first direction may be this one. That's a variance in maximum. After that, the second direction may be this one. But in two-dimensional, you don't have a choice. And the second component is discrete. Okay, but that doesn't give you any gain if your points are two-dimensional and you have two directions. Right? So because there's no dimensional reduction, right? Usually probably will keep only one dimension, right? Because you want to reduce the dimension. Okay, but if you have, let's say, 10 attributes or 100 attributes, that's totally different. Okay, so in that case, when you choose a second unit vector, so the first requirement is W2 and W1 should be orthogonal, right? And the W2 is a unit vector. Okay, and then we want to maximize the variance after mapping to J2. Right? This will give us these equations. This is exactly like before. Okay, this is the variance after mapping to W2. This is like Lagrange constraint induced component. Okay, this is another Lagrange multiply. Okay, Lagrange constraint induced by this. Okay, because this basically says, hey, the inner product between W2 and W1. Any questions? Again, I will have to go a little bit faster today. So taking the derivative, right? So now we want to take derivative. So, this thing as we derived is 2 sigma W2, okay? This thing, if you take derivative W2, it is 2 alpha W2, like before. Take this to derivative, right? So if you remember, so how to get this, it may not be intuitive, right? So you know that you have this formula, alpha transpose x, take derivative x is equal to alpha, right? So then you need to transform this a little bit, right? So this beta W1 transpose W2, okay? Because these two inner product is the same, and then take derivative W2, okay? So if you come back and look at this is exactly the same thing, x is W2, and this alpha transpose is beta W2. So this is equal to beta W because we need to kick out the transpose, okay? Again, so do remember these two formulas, okay? That's all you need to take away after this course for multivariate derivative. Okay? And knowing them and don't know them make a big difference. Beyond that, you can take a textbook, right, the matrix code. But if you don't even memorize these two, then you will not be able to read the machine learning literature. Okay? And interestingly, we will find that beta actually is 0. We will show that in the next slide. Okay, and because of this reason, then by the way, we after taking the derivative set to 0. Okay, that's why we get the maximum. Okay? And then we this equal to this, right? So we get this, and we can show that W2 is the second largest eigenvalue, second eigenvalue, because this is second largest eigenvalue, right? Because this alpha previous one, the largest already used by W1, right? And you still want to maximize the second component. Right? The next choice is the second eigenvector because the second largest eigenvalue is lambda 2. Okay, so now why beta is 0? So this is what we got previously after taking derivative. So we can multiply WT on the left hand side. Okay, this will give us this, and this, and this. Right? Just times WT. Okay, so what we have here is W1, W2 we require them to be orthogonal. So this term is gone. It's 0. Right? This term is gone. Okay. Another thing that you need to pay attention. This is a little bit not so obvious. This is the key in the derivation. Is this term? This term is a scalar. Okay, because it's in the form of quadratic form, right? A row and matrix. Okay. But another thing important, what does it equal to? Right? It's actually here we do a transpose. Okay, so if we do this transpose, right? So this becomes W2 transpose, sigma transpose with sigma itself because it's a symmetric covariance matrix, and W1 transpose. Okay, so because of scalar, it's equal to its transpose. So these two are equivalent. Okay. Now let's look at sigma W1. Right, so we know what is sigma W1. Sigma W1 is exactly lambda 1 W1 because W1 is the eigenvector, right? So after mapping with sigma 1, we get, the first eigenvector times the first eigenvalue. This eigenvalue is eigenvalue. Okay. So what does this mean? This means if you look at this term, we do the transpose, but because of the value anyway, a scalar anyway. And this term is equal to this times this. This is the constant you can move forward. Okay. And again, what is this? This is the orthogonal, right? So this is the. So interestingly, this term is also there. Okay. So both terms are there. Right. And this is what? This is 1. Right. The unit vector. So the only choice for your beta times something that is 1, right? Equal to 0 minus beta is 0. Okay. So that's why we have beta 0 and you can continue with this process. Okay, you can continue with this, and you will see that sigma W3 is the third eigenvector, and the alpha 3, the lambda 3 is the second largest eigenvector. Okay, you do this again and again. So this is the way you derive it. And let's put things together. Right? So what is PCA doing? PCA is actually, so far we assume the data is centered. Usually we will center data. Okay, so let's say your data point is not along the center. Right? So most of the machine learning will do normalization. So we'll pull this to the center. So their center is exactly 0. Okay, so we'll minus this mean here. That's this n. Okay, and then so this after minus this data, after shifting to the center, okay, we will always assume this. So our previous derivation assumes this center. Okay. So then after the center data, we are doing dimensionality extraction, also dimensional reduction. We do a linear transformation of the original, axis, right? So the original point. And we'll get z. These are the new coordinates. This may be the old coordinates in your table. X1, X2, X3, the values. After transformation, you will get a new table. Z1, Z2, Zk. Okay? Originally it's XD. And they are the new coordinates in the new dimension. Okay? So this is what we are doing. And all we do is just linear transformation. I think you already get it that these are relevant to W1, W2, W3 that we derived before. So you can get intuition. So let's ignore, assume the data is already centered. So how do we see that? So this is actually not difficult. Okay, so if you think about the X is your data item, okay, right? And W is what? W transpose. So W transpose is more like columns of W are the eigenvectors, right? So W is what? W is W1, W2. But we are using block matrix notation. Okay, we assume this WK. So each is a column. So this whole thing is a matrix. And we are transpose. After transpose, it's W1 transpose, W2 transpose, and W3 transpose. Okay. And we are saying, hey, this guy is equal to Z. So if you write it out, this is X. So let's write this out. This is your maybe X1, okay? This is a coordinate XD, right? And this is your new dimension, Z1, Zk, right? So let's see what's the relationship, right? So if you can easily see that, this is the first row times the first column, right? Equal to Z1, okay? The second row times the first column equal to Z2, right? So you only have one column, right? So basically we are saying Zj, okay, a particular J here, is equal to the Jth row, which is equal to Wj transpose times your S. Okay, so this is basically how you get, this is exactly what we see. So this is exactly this thing. Right? So W1 get to Z1, W2 get to Z2. Okay. So this is how you can see this actually in matrix form. And so we are centering the data so that the original data is like this. We center it like this. You can even, rotation is done by this W. Okay. After rotation, you get into Z space, which is actually say most component along this direction, a little bit of component along that direction. Right? And then you can say, hey, this is the original data point. But now the major coordinates can be categorized as one. I will drop the 2. Okay. This is also what we will see in our assignment. So because the variance of Z2 is too small, right? So it's not so important. Almost no variance. Okay, then we can drop it. We reduce the dimensionality from a 2-dimensional space x1, x2 to 1-dimensional space, which is the. So how to choose K? Right. So this is a question. Right. So what we will do is, remember what we basically, put simply, what we actually are doing is doing eigen decomposition on sigma. Okay. So what is PCA actually doing? Firstly, you will compute your, because you have the data, right? You can compute a covariance matrix on your data. Okay. So covariance matrix is computed, I think, by this, right? These X are your data, and the mu is the center of the data. And you will use this formula to compute your covariance matrix. Of course, this is not expected parameter. It's a sample covariance matrix. Okay. After you get sigma, what you do is you do eigen decomposition. Right? So we just show you how to do eigen decomposition. Right? It's a P, D, P transpose. Okay. And then you will get those eigenvectors and through with the eigenvalues. Okay. So after that, so these are the first eigenvalue, second eigenvalue, third eigenvalue. And as we explained, these are the variance. Right? So basically your data variance, right, can be decomposed, your original data variance can be decomposed along these 2 directions. Right? So this first component, second component. Because they are orthogonal, their variance can be added. Okay, there's no overlap between them. Okay, it's truly, if you compute, for example, if you compute your 2-dimensional data points variance, it's really equal to the variance of along Z1 plus variance along Z2, which is lambda 1 plus Z2, because they are orthogonal. Right? You can easily prove this. And I think if you in probability theory you also know that if your variance, if your 2-dimension, right, Z1 and Z2 are orthogonal, right, you can add the variance. Right? If they are not orthogonal, you cannot. Basically, we are saying variance of Z1 plus Z2 equal to variance of Z1 plus variance of Z2. Okay. So they can, because the new dimensions, Z1, Z2, Z3 are orthogonal. It's really the variance, sum of the variance of the data X is really the variance of each dimension, Z1, Z2, Z3 added together. Okay. Now, so this is what we want to say. So if you do dimension reduction, you still get the D dimension. It doesn't help, right? So no, we have a D by D matrix, which is sigma. Right? After dimension reduction, you will get, as we said, P and the diagonal and the P transpose. Okay? And this is D by D. Okay, right? So this is not so interesting, right? Usually we will see, hey, these are from large to small, right? If this already captured most of these, right? So these are almost 0, right? The rest of them are 0. 0.001, 0.002, etc. Okay, and then we can reduce it. Right? We say, hey, this is our key information. Right? We can drop these. These are noise. And if you look at the dimension here, as we said, this is W1, W2, WK. Right? So these are key dimensions associated with these eigenvalues. Okay, the rest dimensions are noise introduced, but we drop them along with those coordinate values. Okay. So a typical way to choose lambda is firstly you solve them, of course, right? Then this is called a proportional variance, right? So you say, hey, I want 90% of the error to be captured. The rest we can drop. Maybe they're noise. Okay. The ideal case is if your 90% of the variance are captured by only those small dimensions before, like 10 dimensions. So the rest maybe 990 dimensions can be dropped because they're noise. Most information are already hidden in the first 10 dimensions. So we use a scree graph to pick K. It's also called Abel method. If you know the K means, right, you choose K, it's the same. Okay. It's Abel method. So if you look at eigenvalues, initially big, and then lambda 1, lambda 2, and then later maybe lambda 30 is already 0.001, etc. You don't really need them. They are potentially caused by noise dimensions. Okay. And you cut somewhere. Okay, so here, for example, if you look at the percentage variance, 90, you cut here, maybe it's 25 dimensions. Earlier, you may have 70 dimensions, or maybe it's 64 dimensions. Okay, and here is an example. If you you have optical digits, like a administered set, right? So you have images, right? And those images are very high dimension, right? So if you have 28 by 28, it's 28 times 28 dimensions, okay? And for that image, you can do a PCA over those dimensions, maybe 500 dimensions, okay? And then after that, you want to reduce to only 2 dimensions, right? So here's an example where we go from maybe 28 by 28, which may be 600, right? So I don't know that, maybe larger, okay? Reduce to only 2 dimensions, right? After doing that, okay, go from number of pixels, right? So maybe 600, go all the way just UPCA to 2 dimensions. What do you find? Hey, it actually makes sense, right? So you can, all the 4 numbers are around this direction, 6 are around this direction, 3 are along this direction. So this basically says actually only these 2 dimensions already capture most of the information, right? So using these 2 components, you can already cut out 6 and 4 from the other next 3. If you go even more, right? So you get the first 10 dimensions, right? So it's almost there. You get everything, right? Because we altogether only have 10 digits. Maybe each dimension can describe 1 digit. Okay. So that's it. Yeah. So next is factor analysis. Okay. The reason we talk about factor analysis is its derivation is a little bit different from principal analysis, right? So PC, principal component analysis. It's actually reverse direction. But this process allows us to be more flexible, right? So we can do a PPCA, etc., other methods. Okay, it's a uniform framework where PCA is just the simplest form of factor analysis. Okay, let's take a look at what factor analysis is doing. And keep in mind, we are just doing a linear transformation from the original space X to a new space Z. Okay, D-dimensional to K-dimensional. So factor analysis assumes there's a set of latent factors, Z1, Z2 to Zk, right? And because of these latent factors, they're generating the data. The data can be high dimensional, D-dimensional, but it's actually generated by only a small fraction, okay? A small fraction. So this is also like a low rank tensor or matrix decomposition, right? So if you know that. So we assume always a small number of factors is influence the data, right? Even though you can generate numerous data, okay? That's also if you know the generator model for like a GAN model, generate human faces, right? Assume the model is limited, you have unlimited number of possibilities of face. So you can use some hidden components, hidden factors to describe the entire data set. Okay? You want to find those things. Right. So this is, again, dimension reduction following the same idea. Right? So maybe only these transformed 10 features can describe all the 1,000 features. Right? The other features are redundant in some way. Maybe the first feature X, the 10th feature is X squared, the third feature is cubic, they are kind of redundant. Or the fourth feature is X1 plus X2. Right? So you want to get rid of them. Okay? And the goal of FA is to characterize the dependency. So usually it's not for dimension reduction. We will explore later, okay? Among the observed variables by means of a smaller number factor, right? If you have 1,000, but actually they can be described by only 10 factors. So the problem setting like this, we have a sample data points like before, right? But we don't know how the data is generated from which probability density function, right? But we know that there's a probability density function generated data, and the expectation, the mean is mu, and the covariance matrix of the data is sigma. Right? So it's like for example, if you distribute Gaussian, then it's a Gaussian, high dimensional Gaussian with mu and a sigma. Okay. And the important assumption is this, right? So the factors should be orthogonal, right? So it's more like you assuming the real world how to generate human face, right? So maybe you have the race, right? So and then you have the hair color, right? So you know age, right? So the orthogonal dimensions, right? So you think about the race and the age, they're orthogonal, right? And then so you know the covariance is 0, right? So your age and your race, they're orthogonal, right? So whatever your race is, you can always be at that age. Right? So at that age, you have all kinds of races. Okay, so this is the covariance is independent, so which means the covariance is 0, variance is 1, because we want to normalize the factors. Right? It's a unit vector. So you say, hey, this is 10 times the age, right? If I'm 10, you give 100, right? So that's fine, but you can normalize it to 10. Right? So, and this is expectation. Okay, so this expectation is 0. Okay, so we assume the data is centered. Okay, the factor is centered. Maybe if you think a human age is from 0 to 100, then this is more like you minus 50, right? And divide by 50. Yeah. So it's standardized to 0 mean and standard deviation 1. Okay. And additionally, along each dimension, we also have some noise. Okay. The noise is white noise, which means it's not a systematic noise. Right? So there's no bias. So overall, the noise will cancel each other. Right? So if you pile enough. So the expectation is 0, but the variance, how severe is the noise? Right? So this is variance. Again, because we assume they are on different dimensions, right? So the noise are on different dimensions. Okay, so they are orthogonal. So the covariance is 0, and we assume the noise and the noise is on a different dimension from other components. Right? So if for example, we assume the hidden factors are Z1, Z2, Z3. Okay, they are orthogonal. And in that case, my noise epsilon 1 is only along sigma 1. If it's covariance with sigma 2 and it's sigma 3, that's it. Okay. So with this assumption, now we can model the actual data you see. That X is actually a linear transformation of those factors. Okay. The linear transformation and inner product, the weights for that particular highest dimension of the data, and those k k factors. Right? And you assume always use standard data, okay, minus mu. After standard data, it's equal to the inner product between Z, right, so Z hidden factors, and some weight vector associated with your ith dimension of data. Okay? But there's some noise along this ith dimension. Okay? So actually, if you look at the sigma, sigma is actually associated with the data dimension. So my description is wrong. Okay, so the sigma is for noise is along your data dimension. This makes sense because when you have the table, each dimension you introduce noise. It's not with the hidden factors. Okay? Figure factors have no noise; they are clean. And so, without loss of generalization, we assume the data is centered. So we can get rid of minus mu I. And here's here is a description. Right? So previously we say that we are going from here back to here, right? Now we assume a generative process. Well, we have the hidden factors that actually generates data, actually affects the data. Okay? And it's generating this data you see. Okay, so this is a reverse process from PCA. Again, this is by rotation, by the rotation matrix W, and the translation. Translation is this is a rotation translation by the mu, which we center. So any questions so far? If not, we will continue. Right, so yeah, today we may not take break because it's the last class. We need to finish 50 slides. The direction of factor analysis is object to that PCA. Right? So PCA, if you have seen the data, you want to map to different dimensions to maximize the variance along each dimension. This is PCA. Right? And factor analysis assumes there's a really key hidden factors that really regulate your data, how data is generated. Right? So you time a data matrix V and it generates the data. Right? So the V is basically this. Right? So these are the V's. If you know the linear equation, right? So the linear equation form is something like this. Okay, V times 3. Right. So Yeah, so this is PCA, this is factor analysis. Let's go back to the factor analysis formula before. Okay, I mean this formula. This formula. Right. Now we want to compute the variance. Remember, we assume this is 0. Okay, and how can we compute this? So we can actually compute like this. It's really very simple. We know that the covariance between Zj themselves for different j's are independent. Okay, and Zj and sigma I are also independent. So when your variables are independent, the variance are addable, which means if your variance, let me, if you have variance of variable a plus b, it can be equal to variance of a plus variance. Okay, so this only when a and b are independent. Okay, so this is our assumption. So and another important rule you need to know is the variance of CA, where C is a scalar constant, right, is equal to C squared. Okay, so that's why you have to square. Right. And we know that the factors are normalized, so they are 1. So we will get this thing is the variance. So so the first part of variance is explained by the common factor. So the common factor say. And the second part is the variance specifics. So this variance is something that is introduced. This is scalar. Okay? This is introduced by when you measure your data on the ith attribute. So when you measure age, maybe there's some, you make an integer, right? Maybe 88 or 28, but you have so many months. So maybe it's closer to 29 already. So that's kind of noise that you can imagine for your data. Okay, so now let's go back to the covariant matrix X. Right? So the covariant matrix X can be written like this, okay? Because of this reason. So because of the so we are working with the covariant matrix. So this is what we are talking about. X is equal to this, right? Because we assume it's centered. Otherwise, you need to minus me. Right? So now let's look at the covariance of your data, right? And we replace X with this. And we know that these components and this noise are totally independent. They and sigma are orthogonal space. It's like you are in these 2 dimensions. I'm in this dimension. Sigma is in this Z1 data. Okay, so they are orthogonal. Right. So then we can just write it as summation. Write as summation because we just explained why. Right. And this thing is basically the sigma. This is a diagonal. Okay, so this is a diagonal. Right. This is phi 1, phi 2. So this is exactly these phi's on the diagonal. Okay. Because if you look at this is covariance matrix, right? So you know that sigma themselves are independent. Right. So this is really saying, hey, this is sigma 1, sigma 2, sigma 1, sigma 2. Right. So this is your sigma 1. This is your sigma 2. Right. If you look at sigma 1, sigma 2, this is it. Okay, this is our assumption. So that's why this is diagonal matrix. And on the other hand, we can show that if you have some form like this, right, it takes this V out. Here V is a fixed transformation, just like our W. Okay, it's equal to something like this. Okay? And we will show this in the next few slides. Okay, if you assume this is correct, then this covariance there. Right? So this covariance there is 1. We normalize the factor. Okay, so we have V transpose. So we finally get sigma equal to V transpose. Okay. So a similarity of this is actually something we just show you. It's a variance of Cx. Right? It's equal to what? It's to C square variance of X. But now the complication is now it's not X, it's a X vector. Okay. What if your X is vector, right? So then if your X has constant C, right? So this could be a matrix now. Okay, with a linear transformation. But when you take it out, it's still square. But this square is nothing simple, right? If you look at here, it's like a quadratic form, right? It's a different kind of quadratic form, right? The previous quadratic form is a vector. Right? This is like a vector, row vector, like it's transpose, this is X. Now it's a matrix, but it's similar to when you take the constant matrix out, it's a quadratic. Okay? Let's see why this is the case. So it's a generalization, right? Previously, when we talked about variance of a random variable, it's a scalar variable. Right now, we are talking about a vector. Okay, so here we have some notation issue. Right? So this is not a matrix. When we talk about this is really X vector. We go to X1, okay. K by 1. Now, if you look at the original variance, right? So if we generalize to this variance, we know that this is actually the covariance matrix, right? Okay, and it's equal to inner product. Okay, it's this form. This we have covered that earlier, so I will not get into detail. This expectation can take inside. Inner product is really, this is I, this is J. So each item. Okay, and you can write it like this. Now we look at if we extend this variance from scalar to vector, what we have. Right? So the first property is this. Right? So remember, X is what? X is the vector. Okay, it's not a matrix. So then we have something like this. If you remember previously, we have scalar. So this is equal to X squared minus E squared. Okay? So this is exactly because transpose is itself. Now, in the general form, if X is a vector, we have something like this. So the proof is something like this, following the definition, variance is equal to this, auto product, and then you can time them out. So this X transpose here is minus EX, this X times minus EX transpose. And this term is the EX times X transpose. And finally, the minus EX transpose. So this is the proof. And then you remember outside we have expectation, we can take inside. But this expectation already constant, you can take out. So this expectation EX, this is EX transpose. Okay? And these three terms are the same. It's just a minus something, and plus back something. Right? So it's like a minus one something. Okay? And this gives you this form. So just follow this definition, you can prove this theorem. The second is if you add a vector, random variable, but a constant vector. It's still, the variance doesn't change. So again, this is vector. Okay, some notation is not so clear, but it's not. So following the definition of this, but you replace X with A plus X, you will get this, right? And you can see if this A is a constant, so EA is A itself. And so this actually can cancel. So this is the same. Okay? And finally, we'll get back this. So this is again the variance X. Okay. So finally, is what we have here. Right? So what if this is a linear transformation? X is a vector, this is a matrix, right? And we will get this. Okay. So here it's a confusing. B becomes a scalar chemistry, right? But it's really a matrix. X is a vector. Okay. Don't get confused. And following the definition, so we just replace X with Bx. We have this definition, and so B is a constant matrix. Because of this reason, we can take it out. So B is taken out. And because this is what? This is, sorry. Let me see. We should have sufficient time. So let's do something. So this is B, again, this is a matrix. Okay. X minus expectation X. The whole thing, right? Take transpose. Okay. So that's why after this, you reverse the shape. Okay, so we got this. And again, remember B is a constant matrix, so you can take them out and you get this. And what is this? This thing is your range for the definition. So that's why you have a matrix and matrix transpose. Okay. This is like if you're a scalar case, this is the Cx, right? So you have C squared X. You can also write it like variance X and C. That's C squared. This is a generalization to vectors. Okay. Right, so in general, so what you need to take away is this rule. Right? So if you have a vector X, right, a time of matrix A, and additionally plus another vector A, right? So plus a constant and change the variance, plus this A, if you take it out, you need to time A and A transpose at the end. Any questions? Yeah, if not, we will continue. Right, so that's why we basically, the purpose we are talking about these slides is to prepare you for this. Right? So you have this from here to here, basically explaining. Yeah, because I assume you don't have this math background, and in the future you can directly do it. Right now we develop. Okay. So it's essentially this conclusion. Okay, so now let's get some intuition of factor analysis. Right, so let's assume your data, original data is still two-dimensional. Right? It's a column vector. Usually we will write it as a row vector. Right? So because you don't want your it's occupy many rows. You write a row vector, but you say it's a column. Right? So it's transport. Okay. And then you have the V. So this is a transformation from X to Z. Okay. The covariance matrix can, as we said, sigma equal to V transport plus the diagonal phi. Okay, so it's something like this, right? So now let's look at a particular case. Right? So get some intuition. Right? So sigma is really something like this. Right? So if you look at this corner, okay, so this corner, what is this? This is really the first row times the second column plus 3. Right? So this is really this item times this item, which is here, and this item times this item, which is here. Okay. Oh, no, sorry. Let me see. Yeah, it's correct. That's this item, this item, this item. Okay. Now let's think about when our sigma ij, sigma 1, 2 will have a high covariance. Right? So by the way, this is computed from your data. You have a bunch of data and you compute the covariance of these two columns according to so many values of the data. And then you find, hey, these values have a very high covariance. Why? So the only possibility is either this is high or this is high. So that means either both 1, 1 and 2, 1 is high. This means, for your x1, x2, right? So how to say this? 1, 1 and 2, 1. So this is the first, this is V1. Right? The data are high on both on the first factor, okay, Z1. Right? So they are both high on Z1. And the second is really, these two are high, which means both x1, x2 are high on Z2. Right? It's the second factor, okay? And only in this case, or either, at least you should be high on one factor, then your covariance will be. Okay? And if your covariance finally found out close to 0, right? And that basically means if this guy is high, but this guy is low. Right? If this is low, this is high. So, I mean, this is high, this is low. Right? If you have something 100, right, then this is going to be big unless you time something very small, 10 to the negative 4. So that means something is really zero. Okay? So these products are not so correlated. Okay? So this is intuition when your data, you will observe a high covariance. That's really relative to the factors. Right? If your data factors are all high on that dimension, then your covariance will be high. Okay? So these factors make sense. And so factor loadings. So here actually we get the relationship, okay, between the data and how you compute the V. Okay, so let's take a look how you can do that. Right, so x1 and z1, how we compute this, right? And using the previous formula, right? So using this formula, only two dimension, we know that x1 is really V11 times the first factor plus V2 plus the second factor plus the noise on your x1 dimension, right? Times z1. And important thing is that these are independent. Okay, so you can say, hey, this covariance of this plus this covariance of this and covariance of this. So you can say it's equal to covariance this with this, this with this, this with this, sum together. Okay, but unfortunately, these two terms are gone, right? Because Z2 and Z1 are independent. Sigma 1 and Z1 are also independent. So only left with this term. Okay, this Z1 echoes with Z1. Okay, and we know that we can take this out, right? So here we don't need square, right? Because covariance is like 2 of this, right? So this term has no V1. Okay, you can take this out, and this becomes variance of Z1. Right? And we know that variance of Z1 is 1. Right? We assume the factor is normalized. Okay, it's a unit dimension. Right? So then we get V1. So what does this mean? This means that V11 is really the covariance between your X1, the first column of your data, and the first column of your dimension reduced data attribute. Okay, so this is V1. Right? And similarly, you can do the derivation. You will find also true. So that means, what does V mean? Right? So V should have a physical meaning. Right? It's really the covariance matrix. Okay, between this your old dimension and your new dimension after dimension reduction. Okay, so this is telling you what the loading matrix really means, right? Because originally we just say, hey, originally we assume we have this relationship. Right? So what is V? V is really the covariance matrix between X and Z. Okay, so that's what V is. I think I should be able to go one step to the. Yeah. Okay, so next is dimensionality reduction. Right, so given S, right? So S is because what we see is the actual data, right? So it's a sample from the ground truth signal. Okay, so this is sample covariance matrix. Right? This is all we can get, right? So what we want is we want to find the V and the noise, right? And phi, and we want this to be close to this, right? So because this is sample, so we just want to approximate it because there will be some noise. Okay. So if there are only a few factors, so then we can get a simplified structure for us. Okay, because this if you think about it, the ultimate goal is you don't want to Z1 to ZD, right? So you want to Z1 to ZK, right? And if you realize there are only K factors, right, then your S is actually simplified. So you don't really need all those data to compute. So the number of parameters will be reduced from, originally if you have a D by D matrix, right? But it's symmetric. You only need a up triangle or down triangle along with the diagonal. Right? You will have so many parameters. Now you only need these numbers. The reason is very simple, right? Because originally your S is a covariance matrix, a D by D. Right? So how X1 and XD are correlated. Okay? Now we tell you this. Right? So this thing, V is what? V is Z1, Z2, Zk. Okay, so this is K dimension. Okay? And V transpose is what? Is Z1, Z2, Zk. So V transpose. Right? So the time this is D by K, K by D. Right? So this is why you get D by K. Right? So this is only described by K features. Right? So now you can describe the S instead of D square. Right? You can just use this is D times K. This is D times K, right? This is K times D. Okay? So this is, but again, this is the same thing as V transpose. So you only need D times K plus D. This D cannot be saved because this is a diagonal noise on the data. Okay? So you can reduce from kind of D square to dk in some sense, right? So D square, let's think about 1,000, right? Squared 1 million. Dk is just a 10,000, right? 10 times 1,000. Okay, so that's a huge save of the, the parameters, okay, to describe the data. So as a special case, right? So if you remember our PCA, right? Let's go back to, this is 33. So let's go back to our previous case. Yeah, let's see. Right. If you look, let's assume the mu, by the way, okay, is gone, right? You already sent it. Oh, here we can keep it. It's the same, right? if we find inverse of V there, right? So we will get this. But the difference is, let's say we times the inverse of V here, and this is gone. And this becomes a linear transformation of this, becomes another column vector. So you can see this is really say equal to W. The only difference is that this thing is additional step, which is not there in PCA. Okay. Let me try to go one step to you. Okay. Okay. So this is really PCA is special case of factor. And we also have a different kind of PCA variants. Right? So for example, probabilistic PCA, right? So I think Scikit-learn may also have that, and otherwise there will be some other packaging. Right? So this assumes that if your data has a lot of noise, right, then in that case you really need to model the noise. Right? Then you really want the noise part to also be there. Right? You know that along some dimension you have some noise. Okay. And the probabilistic PCA assumes that all the noises on all dimensions are the same. This makes sense in some cases, some data, right? So for example, your GPS coordinate, you have longitude and latitude, okay? And something like this. Latitude is longitude or something. And then your GPS error is a square. Right? You are here, GPS refers to you are here, you probably are here. Right? So along both dimensions, you have 1 meter error, okay, something like this. So this is called a probabilistic PCA. Okay. There are also other variants of PCA that can go even beyond that. And most of the cases, you are just using the simplified PCA. But the reason you are using simplified PCA is because factor analysis offers no advantage other than interpretability factor. Right? Okay, so because this is a reverse process, right? You can go from factors to the data, and you have some noise. And because if you do PCA, you will drop those noise. Right? So it's kind of this dropping process handling this noise. Okay. Next is last, unsupervised dimensional reduction method. Okay, so called MDS, or multidimensional scaling. I believe you also, some of you at least, seen this in Scikit-learn. Right. So let's look at why we need it. Okay. So the problem formulation is that we know the pairwise distance between pairs of points. Right? So this is actually a little bit confusing, right? If you already have the point coordinates, you of course can compute the Euclidean distance, right? Of course, you can use other distance, like Manhattan distance or Manhattan boundless distance, etc. Okay, so can go super complicated. But anyway, if you have the coordinates, you can always compute the distance. Right? And but the case is where we consider we don't know the coordinates. Maybe they are in some space, but the exact coordinates are not known. And only in this case, we really need an MDS. Right? So there's no point if you do MDS on a relational table because you know there are coordinates already. Okay? And for example, if you are working on a social network, right? So you have user A, user B, they tweet each other, right? And follow relationship. Like Tom follows Mike with 3 hops, right? So distance 3, but there's no coordinate there. Right? So in that case, maybe you can think about, you can embed this distance matrix into maybe 50 dimensions. Assume there's a 50 dimensions there, and then you do MDS to reduce the dimension. Right? So it's like you have a graph capturing the distance, and you want to reduce to a 50-dimensional space. Right? So it's kind of like a word-to-vec, right? But it's for just distance matrix. Right? It's like embedding a graph, each node in a graph into a vector. Okay, so this is one use case for MDS. Right? So you want to embed points in a lower dimensional space, right? Originally, maybe if you use 50 dimension, you can fit those users into these 50 dimensions, assign them coordinates, and their distance exactly the distance on the graph, on the network, okay, for example. But now you think, hey, 50 dimensions is still too much. I want to just 10 dimensions, right? So that's why you use NDS to reduce the dimension. So that being said, of course, we need to specify, hey, I only want a 10 dimensions, okay? So this is a projection into a low dimensional space, but it's not unique. Right? So you can rotate and translation. and you can reflect. I mean, you can do those kind of changes that keeps that distance, right? If you shift it a little bit, translate, right? So Tom and Mike both go left by 1 meter. They are still of the same distance, right? So actually, it's not unique, right? There are a lot of solutions for the low-dimensional coordinates. Okay, so here's the example where you can, let's say you can compute the Earth distance, so on the Earth. So the Earth distance is actually called a Harris-Skin. I don't remember the name. H some distance. Okay, it's a circular shape surface, right? So it's a ball, right? Surface ball. It's not a for that far away, you cannot use a Euclidean distance to compute. Okay, it's a GPS coordinate, and you have some formula to compute the Haverstring distance between. Okay, and then you want to embed these cities into just a two-dimensional space, right? So you can do that using MDS embedding, right? So you can get this. Right, so derivation is something like here, right? Again, we don't know what is a d-dimensional space, original space, but assume that there's a way that we can give them coordinates, right? And then the distance in that dimensional space actually correspond to our distance that we get, let's say on the graph or on the Earth. Okay. Now, let's think about this. Right? So what will be the squared Euclidean distance between 2 points, R and S? Right? So this is the R row and S row in the data set. Okay. So we can compute the Euclidean distance, something like this. Right. So definition, L2 norm squared. Okay. And you can write it like this. Okay. And this thing you can expand it like this. Right? So the A squared minus 2AB plus B squared, B squared. But you have D dimension in the high dimensional space, which you don't know, so how many dimensions and what are coordinates, right? And next, when we are here, let's do something. When we are here, okay, let's define this. So we define dot product between 2 rows in the data. Right? So this is the row matrix. This is S point. This is S point. The inner product defined by this, right? And we call this BR. Okay, BR is the R state point. If you know the coordinates, R row and the S row, the inner product. Then you can see this is the R row inner product itself. This is BRR, and this is BSF. Okay, and this is minus 2 BRs. Right, just following the definition. And yeah, so this is one thing. The second thing that is very important is what is this? Right, so you can describe it using this B matrix. Okay, if you know outer product, it will be much easier for you to get intuition why this is this. Okay, so you think about let's just think about one row. Okay, one column times this transpose. So this is really something like x1 square, x1, x2, x1, xd. This is our product. This is xd squared. Okay, but this is just for what? This is just for one dimension. So, but remember we have this is we have d-dimensional data. Okay, so this is more like we add this kind of a matrix d times. Okay, yeah, then we look at it. So basically, if you look at this X matrix here, so instead of one x1 to xd, and it's actually a matrix. So this was the first row. So this is the last row. Okay, maybe n data. Okay, and this transpose is something that transpose. Okay, this is something like this. So this is row. Okay, and if you look at how you get the item B here, you get item B here, you can see that it's really first row times the first column. Right? So that's why you have the D summation. Right? So this is this times this times this times this. You have the D of it. Okay. So this is the first item and the first item. That's the RRR and the SL1. Okay. This is the first item, the second item. So this R and S are 2. R is 1, S is 2. Okay. So I hope you can get the intuition why this is a generalization of the output. Okay. Right. So this is the matrix generalization of the output. And so what I want to say is, so BRS. So if you think about all the R and S dimensions, so the n of them, it's basically we say that B, just to make it clear. If we define BRS like this, then we have B is equal to, BRS, each element RS. But R and S R has n values, n has n values. Okay? So they are equivalent. Now, we assume this. We'll always center our data. Okay. The reason we want to center our data is in machine learning, we'll always center our data. Okay. Because let's assume support vector machine. Right. So maybe for decision tree you don't need. Right? So it can shift rather than some. But for SVM, neural network, etc., you always need central data. If you think about the deep learning, for example, right? So you need to initialize your data as pixel, you need to divide by 255 or something. Right? So center your data. Okay. And for the next layer, you say, hey, next layer, I'm not centering my data. But you think about the activation layer, right? So for example, 10 edge, sigmoid. Right? You are basically saying whatever number negative infinity to positive infinity. I center them into some range between 0, 1, or -1, and then go to the next layer. So basically, neural network also needs center data. Okay, this is where, for support vector machine and the neural network, centering data is the first step. Okay, so that your data is working. Okay. And if it's not centered, you can get pretty bad performance and can run much longer. So because when you do support vector machine, you assume you are cutting a line. If your data is clustered there, right, so the line, if you draw, the sensitivity to find. The angle is very small. The theta is very small. When you are centered, the theta is almost everywhere. So your parameter W for the line to split them, if you shift a little bit, right, and you sweep all the data, this is not good. If your data is centered, the W shift a little bit in the SVM. It's just a shift a little bit, changing some of the data points from here to there. Okay. Yeah, just keep in mind the neural networks and the SVM center your data first, okay, and better normalize it to standard deviation 1. And decision tree you can go with that because decision tree is different. So you find you find the middle point. So so yeah, assume your data are already centered. Right? Then what we can do is we can sum up equation 1 on R and RS and on both R's. Right. So let's look at what is equation 1. Right. Here's equation 1, and what would we sum up to? For example, sum by R, sum by R. Right. So one thing you need to pay attention is because so we will heavily use this assumption. Okay, that the data is centered. Okay. So when our data is centered, when we sum equation 1, right? So remember, this is left hand side we sum by R. Okay, so this is where we get here left hand side sum by R. The right hand side, this is sum by R. Sum by R of BR, right? So we assume this is sum R by BR, but we assume this is T. Okay, so you have BRR, B11 plus B22 plus B33 plus DNN. It's T. So this part is T. Okay, summation over R of this T. Summation of R over this is n times BSS because BSS is irrelevant to your R. Okay, so if you time this n times, it's n BSS. That's n BSS. So the tricky part is the last one. So this is say, hey, I have this and I sum over R. Okay. So sum over R actually gives you 0. The reason very simple. Right? Originally we have RS together. So but if you add another dimension. Right? So this means for each S, you have the whole range of R summed together. Right? And we know that if you have whole range of summed together, it's 0. Okay? So we can easily see this term when you add over R or either over R or over S, it will be 0. If you over both of them, of course, it's 0. So this term is gone. So we'll get this is equal to T plus MDS. Okay, T is this for simplicity because we don't care about this T. So, and symmetrically, if you sum over S, the third term is gone, and sum over BSS becomes T, sum over BR becomes MBR. Right. And finally, if we, let's say here we can actually don't need to go back to equation 1. And so let's think about this thing. Right. Now we over both R and S. We over R here, we over R. Right. And we know that over R over BRR is T. Right. So this is what? This is NT. Right? And here we have another R over T. Right? But T is a constant. Right? We over R from R equal to 1 to N times. It's another NT. Okay? That's why we have 2 NT here. Any questions? Yeah, we are right on. Now let's define something. Right, so previously we showed you that we can, we sum over R, we sum over S, sum over RS for the scale. So now let's assume sum over R. You just say, hey, I want to sum over R using star tool. In Python, you have a column. Right? So this dimension is summed out. Okay, but we divide by n. So if we divide by n, it's the right-hand side also divide by n. So if you look at what is the right-hand side, we are divided by n. Okay, we'll come back later. Okay, and similarly here we are divided by n. So the right-hand side divided by n. Okay, and here we are taking out both dimensions. Right, so we actually divided by n squared. So because so let me see. You already have. Let's derive it here. Okay, that would make our life a lot easier. Okay. So in the next slide, we have 3 terms. The first is this term. The second is this term. Okay. And the third is this term, n squared. And we look at here. What is this? This T by n plus BSS. This is T BRR. It's T bar. Okay. This is what? This is 2T bar. So what do we see? What do we see? So you see, this is T bar n, this is T bar n, this is 2T bar n. Right? So if you sum equation 1 with equation 2 minus equation 3, so you cancel the T. So if you have 1 plus 2 minus 3, you get what? You get BRR plus BSS. Okay? So this is exactly what we are doing. Times 1, which is the same. Oh, this 1 and 2. Anyway, they are summed together. So 2, 1, 1, 2 doesn't matter. Okay. Minus 3. Okay. So we know this thing is BRR plus BSS. Okay. And minus DRS squared is equal to this 2 BRS. Okay. So this really holds. Okay, 2 BRS. This really holds. Right. So because we previously we say DRS square is really BR plus BSS minus DRS. Okay, so this we need to go back. Right. So this is really this. Right. Basically, we are saying that BRS we will be able to compute BRS as a function of this. Okay. So this is why we have this. Why this is so important? So the reason is that we don't have their, all we have are the distance, right? So how far away from a data point are to data points. We don't have their coordinates in the original space. That's the whole reason why we want to use the MDS, okay? but just based on their distance, here now they are all distance, okay? Just based on the distance, we are able to compute BRs, okay? We are able to compute BRs, right? So you think about it. Previously, we are without a distance, we are using the coordinates, right? We get rid of those coordinates. We directly using a distance, which is what we know, right? And we do care about how similar 2 points are, right? So this is more like their covariance or something. Right? So the covariance matrix, right? So how their dot product are, right? So how similar rho R and rho S is. Right? This is basically a covariance matrix. Okay. This is actually a covariance matrix is n by this. Okay, so you can easily see that. So this is n times the covariance matrix. So but n is constant. So this is basically we're saying that we will be able to compute the covariance matrix B just from the distances. Okay, we don't need to know their coordinates. That's why these 3 slides are what we are doing. We want to show you this. And now that we know that this this covariance matrix is positive semi-definite, right? So it can be expressed as spectral decomposition, right? So this is what we are talking about. So if you remember, so this is PSD. So this is symmetric. Okay, this is a symmetric matrix. If you compute the T, it's still X2. Okay, and then we can do eigen decomposition. Eigen decomposition spectral decomposition is the same because this is diagonal. This is something like this. Okay, and additionally, diagonal matrix can be easily taken square. Right, so if you have a diagonal matrix which is lambda 1, lambda 2, lambda 3, okay, it's equal to what? It's equal to square lambda 1, square lambda 2, square lambda 3 times the same thing. Okay? Because diagonal matrix times diagonal matrix go down. Right? So the first row times the first row is lambda. Okay? The first row times the second row is right? Because this dimension, this is it. This dimension, this is okay. Right? And the second time this is okay. So we can easily, because this is diagonal matrix, we can take the square root of it. Now, if we take square root of it, so basically this is what we get. Okay, firstly, any square matrix can do eigen decomposition, right? And then any diagonal matrix, we can take square root. Okay? And then for this thing, we can write it like this. Because this diagonal matrix transpose is still a diagonal matrix. So I transpose the I. Okay? So now we got something like B can be written like this, right? So and B is also this, right? So we can approximate X is equal to C D squared. Okay, we can say something like this. Right? And we know that C is what? C are the column vectors. Right? So C are the column vectors. Okay, so of B. Right? So all we need to do is we can use these distances. We know the distance matrix between the different data points to compute this B matrix, right? And then we can do a eigen decomposition on the B matrix. Right? So PCA is doing the same thing, but we use coordinates to compute. But MDS, when we compute the covariance matrix, we are using the distance. Right? We don't know the coordinates. Right? So that's the difference. And once we compute it, right? So we can take the first K major components, we throw out the others that are nodes, right? And this is saying that instead of taking all the dimensions, so we throw out those very small zeros, right? And we take out these. Okay, we just take out these major components, and we'll cover X. Right? So this is basically we are doing dimensional reduction. We only have the K dimension. They want to okay. We are not using all the dimensions. All right. So we can think about it as a low rank approximation of the original data matrix. Let's see D lambda 2 is low rank approximation. Okay, and if you think about the eigenvalue associated with the Cj, the J's column, the J's eigenvector. So this J's largest eigenvalue. Okay, so we actually have this relationship. Right? So eigenvalue times the square root. This is following this equation. Okay, so we know that X is equal to this, right? And then we can derive this. But this is no longer X. This is Z after dimensional reduction. Okay, right? Because we only take the first case. Because this is diagonal matrix, right? You can easily see it. Right? So if you think about the first C, right? First C, second C, third C, and the diagonal matrix. Right? This is like scaling each column like this. So when you time diagonal matrix on the right, it's scaling the columns. Times on the left, it's scaling the rows. Okay, so you can easily derive it by block matrix notation. So for example, if you have, I will not derive this. This is the conclusion. So if you are, your diagonal is all ones. You are scaling each by one, but it's yourself. So this is some matrix conclusion. We can derive this by block matrix notations, but it will take time. And so that's what we have here. So basically, you use your distance to compute B, right? You don't need the coordinates. And once you have a B, you do actually composition B, and you will get to C, and also the diagonal is D. Right? And you compute C and the D 1 by 2, right? And then you will get to C. And these are the new coordinates after eigendecomposition. Oh no, after MDS, dimensional reduction. Okay, so that's if you are doing in scikit-learn. Scikit-learn is doing all these things. Any questions? If not, we need to move on. So the last thing is a little bit more complicated. It's called the linear discriminant analysis, LDA. Okay, so LDA is only dimensional reduction method that we described that is supervised, which means no longer not only that you need X, you also need Y. Okay, so LDA is supervised, and it's really for classification problem, right? So it's not for regression. Okay, and our goal is really wanna hey, these belong to class 1, the others belong to class 2, and you want to do a dimensional reduction of your X so that, those class 1 nodes are clustered in here and class 2 nodes are clustered there, right? So then your feature is more more informative in differentiating these two classes, okay? So here's a case after you do LDA, right? So here's 7, here's 4, right? Here's 0, 3, right? So let me see. If you compare with this, with PCA, you can see this is actually much better. So 0 here, PCA still have some mix. Although we have 1 and 9 mix, but this is already much better. Okay, if you do LDA to 2 dimensions. Right? So this is what we call the free launch. Right? So when you have free launch, you take it. Right? For example, if you originally are just doing data exploration, you only have X, you do a PCA. Right? If you also have Y, of course, you will use the Y of each row to help you, right? Because the ultimate goal is to get your Y for new data. Right? So you need to utilize the Y in the training data, also to do dimensional reduction. In addition to later, you after dimension reduce, you do the training. Okay. You want to use Y also to help you decide the dimensions, like W1, W2 in PCA, right? So this is also the same as in all branches of machine learning. For example, if you look at LSTM model, right? So this is a sequence model where you have a sequence of X. Right? So you give it, and it emits a class Y. Right? So we will not cover that, but no. So this is actually used in time series estimation. Right? You see the history, you create mass points. Or you sentiment analysis. You read the whole sentence and you say, hey, whether it's positive or negative. Right? But what if, in time series prediction, you cannot look into the future. It's cheating. But in natural language processing, you can always look into the future. Right? So you first see the sentence, and then you see whether it's positive or negative. So then they will also have another direction. Okay? This is called a free launch. Right? You can, when you have the sentence, you will always use bidirectional. But if you look at those days, it has the transformer model, BERT, etc. Transform itself to bidirectional. Okay, it's different from LSTM using so-called attention mechanism. But when you see the entire sentence, of course, you want to use both directions to help. Right? Similarly, if you are doing classification, you know why you will always use LDA, not using PCA. Okay. And let me see. So the two-class case. Right, so we first think about the simple case. Right, so we have X and Y. 1 is positive class, 0 is negative class. Right, so, and we want to find a vector W on which data are projected, such that examples from, C1, C2 are well separated. much as possible, right? Because we already have y. We want to also utilize y. So our projection is like PCA, right? But we want to utilize y. Okay. So what we will do is here we are computing sample mean and sample variance, right? So here you can think about y as an indicator variable. Right? So let's assume you have, let's say, you have 10 data sets, right? So these 4 are positive, okay? And there are 6 are negative, okay? So what we are doing here is that we only consider those 4 for the positive ones, right? Negative will be 0, okay? And this is an indicator. If you are positive, I will consider this item. If negative, we are not considering. This is like we are computing the mean in group 1, okay, positive. This is the reverse, right? This is the indicator for negative class, because if you are positive class, this will be 0, negative 1. So we are computing the mean of the second class, okay? So we can write this as WT times M1, WT times M2. So because this is M1, the positive class mean, this negative class mean. But we will take this constant out, right? So because we'll transform them. So pictographically, we are doing something like here, okay? So how do we say, let's say, whether this direction is good or not? Right? So for example, here, it's purely this direction is pretty good. Right? So intuitively, here's what we want to say, okay? If for this class, it's kind of all clustered around M1. And for this class, all clustered around M2, right? So then this direction can describe class 1 and class 2 quite well, right? So it's not a kind of, spread some cross also goes here, right? It's not. In the meanwhile, you want this part to be separate as much as possible, right? You don't want these two to be mixed. If there are variance, these two variants are small, but the entire variance is big. Right? So always say the mean, the distance between two mean are big. Then this is good after projection for this classification task. Okay, you can easily, according to this dimension, we can easily classify. So we say, hey, if you are, let me see time, should have enough time. If this is the middle point, right? So if your value is less than n, then you are class 1, larger than n, or class 2. The incursion. So we have the between class scatter. Okay, so and we also have the within class scatter. This is what we are talking about. Right? So this is within class scatter, within one class. We also have between class scatter, defined from M1 and M2. Okay. So firstly, let's look at what is the between class scatter. Right. So it's really you map your two class centers to this direction, M1 and M2. Okay. And after mapping become the scalar along this direction. Right? And we want this distance square to be as large as possible. We want them to be far apart. Right? So if these two, these two are far apart, right? Then you can easily find a value here to cut them off. Right? So this is easier for your classification after doing this transformation. But right, so yeah, not but okay. So there's another requirement we will see in the next slide. Okay, so here between class scatter, basically, this is this mean in class 1 mapping to this direction, this class 2 mapping to this. Right, so we can write it along like this. I will not repeat this derivation, but you can just take a WT out and for the second part, right, and then do the transport, you will get something. Right. So this thing is a outer product of the difference of the mean, right? And the out product gives you a matrix. Okay, so we will write this between class scatter, this matrix as B. This between. Okay, this is one thing. The next thing is called the within class scatter. Right, so within class scatter is exactly the variance. This is the mean, and this is the variance. Right, so we will compute the variance. Okay, so the variance is similarly computed. Right, so this, if your each data point mapped to W is this coordinate, this is your central coordinate, and the square, and this is added over all the data points. But we only add those, this is indicator for classifier, right? So, and then you can do some similar derivation with this part, just because this is WT times M1. You can take a WT out and then, you know, takes a transpose, right? So you can get this. So, you know, so I think it's better to do some derivation. Let's do the minus. If it's minus WT and 1, right? Square is times this again, okay? But times this guy, you know, this is inner product. So this is equal to what? This is equal to x times WT, right? Minus N1, okay? And you can take this W out. Right, so this WT can take out. So this gives you this, right? This transpose can take it. Right, so this is the value. Of course, this YL should be here. It's like a select operation in SQL language. Okay, so let me see if we have sufficient time. I need to write okay. All right, so we can write, you know, this part times this part. We can time this from, because this is scalar, right? And if you take this as S1, you will get this. Right, so similarly for the other class, you will get this. The difference is that the selection operation is on the negative class, okay? And now we are doing this, right? So just the variance of both class summed together, right? So will be equal to this, because you know, one is this thing, one is this thing. Right? So you can take their summation, it will be this. Okay, so we use W here because this is within class scatter. Okay, so we want a within class scatter to be small. Right? So their variance is small in each class, but the between class scatter to be big. Okay. So this is actually, we use a Fisher's linear discriminant principle. Right? So this is what we have here. This is exactly what we're talking about. Right? So we want this Fisher's criteria. This is also called the generalized Rayleigh for quotient. Right? So this is quotient divide. So to be maximized. Right? So if your between class difference is big and within each class your variance is small, then this guy will be okay. And we show that this is SB, this is SW. So basically, we wanna do an optimizing function that maximizes JW, which is the quotient of between and within two components. Okay. By the way, these are the you know, projective forms. Yeah, both are scalars. Okay. And another thing you need to pay attention is that those things can be easily computed from your data, as XL and Y. That's these are all from the data. So from the data, you will be able to compute SB and SW, right? And then you can construct the function like JW, right? And then you want to find this particular W, right? So you can have all kinds of W directions, okay? You want to find a particular unit factor W such that your quotient here is maximized. Right, so taking derivative of J set to 0, you will get this. Okay, we can take a look at it here. Let me see how to do this. So just want to make sure you can see this right. Can you see this slide? Can you see this web page?
Yes.
Okay. Let me enlarge it a little bit. So we are trying to, you know, we are trying to find a W that will maximize this RW. Okay. So how can we do that? Right. So this is you know, following our multiplication formula. Let me see whether we have time to do that. Otherwise, you can read this offline. Right. So you know, this is equal to what? This is equal to fx times GW. Okay, this is actually W. Okay? Well, FW is we can write it like this. Okay, and GW we can write it like V. Okay, right. So then it's equal to what? If you take a derivative, it's a F prime G and G prime F G prime. Some okay, and if you take this derivative over W, it's what? It's 2AW, right? So because A is symmetric, because it's according to our derivation. Okay? And this is 2AW, right? So, but this is F prime times G. G is what? G is divided by W B. Just transfer. Okay. Now let's consider F G prime. F is what? F is this. Okay. So we have another term which is WT A. Right? But we have this thing, G prime. Right? So inverse of something is negative this thing squared. And so we have WT B W squared. But after that, we need to go in a chain rule. Mu take a derivative. Right? So if we do that, it is a 2B times 2B. Okay. Now, if we compute the summation of these two, it will be something like this. Okay, because this AW, because this is no square, you need to times the square thing here. Okay, and the BW, so because this is a scalar. The scalar you can time it to the back. It's the same. Okay, so we have 2BW and this. Right. So let me clear it. It's a little bit complicated. So you can see even here, we're always doing something like projective form to get a derivative. So if you know these functions, you will be able to read the complicated machine learning literature. So like this one. Okay, so yeah, so we set this equal to 0 because it's derivative set to 0. We want to maximize this out. Okay? And this is a scalar square. So we basically say these two should be equal. We can do. So we want these two to be equal. Right? And remember, these are projective form. They are numbers. They are scalar. Right? So we can divide it. Okay? So we got this one. Right? And what's interesting here is this thing itself is exactly RW. Right? So we can write it RW. Okay? So this RW we can also call it lambda. Right? So we want to maximize RW. Want to find the eigenvalue that is largest. Okay? But there's some difference, right? So this is called a generalized eigenvalue. It's a little bit different from the regular eigenvalue. Okay? So now let's go back. Let's see. Let me do this. Okay, so yeah, I think we are close. Okay, so this is what we derived previously. Okay, and to see why SB is symmetric, for example, right? So it's not difficult. Right? So think about this thing transpose. It's what? It's this thing transpose. That's M1 and M2 transpose times this thing transpose. Okay, so it's itself. It's still SB. So this is symmetric. Okay? And now, this thing you may not see it why it's an eigenvalue decomposition. Right? It's not so obvious. But if you think about it, eigenvalue decomposition really don't have this SW, right? So if you think of this SW invertible, right? So what you can do is you can take an inverse of it on both sides. Then this becomes a eigen decomposition. Right? So because this is your matrix, right? Like sigma. Okay. So then you can use a eigen decomposition solver. Otherwise, you need to use a generalized eigen decomposition. So SW, whether it's singular or not. So some of the matrices cannot take inverse because it's not full rank. Okay. Again, this is computed from the data. So depending on data, it's likely to be full rank, and sometimes it's not full rank. Okay. An alternative method is if you look at this two. So for the two class problem, we can also write something like this. Right? So if you remember, we just derived SPW is equal to this. Right? So because SP is equal to this thing, right? We just take the transpose. Right? And now we're looking at SPW because it's on the left hand side. Okay? Now you can see what is this two parts. This two parts is a scalar, right? It's an inner product between two vectors. Okay, it's a scalar, so you can move it ahead. It becomes C. It's a constant. It's scalar. Okay, and in that case, if you go back, right, so this becomes something like CW. Right? So not CW. Okay, it's W is gone. Okay, W is taking the inner. C and more minuses. Right. So now if you can, sorry, for the constancy in the same direction. So basically we say SPW in the same direction as M1 minus M2. So we can get what? We can get W. W is really, let's go back. So basically we just derive this is M1 with some constancy, right? So now what we can do is, SW times W is along this direction, okay? So SB times W and SW times W all along this direction, right? So we can say W is equal to inverse of this, right? So there's a small constant that we throw away, okay? And we know that the within scatter, right, is both class sum, right? The constant is thrown away. So this is our, W is our direction. Right? It's computed totally from data. No matter it's S is coming from data or M is from data. You can compute W totally from the data. Right. So that's actually, this is a little bit complicated, but by a simple derivation here, you can actually get a simpler form. That's actually what maybe scikit-learn is doing. There are also case for more than two classes. Right? So then your indicator variable becomes K class. Okay, so otherwise it's the same. So there's a total within class scatter matrix is just the sum of all the K classes. Okay, and between scatter, so it's for because for different classes you have NI. So sum up to all the data items. Okay, so just sum them together. Here actually we have a trace. Right? So it's almost the same. Right? So if you look at the previous J is something like this, because that time the W is not, it's just one direction. Okay, actually, if you want to make a W, if you want to reduce to K dimensions, right? So the previous one, if you have more than one vector, right? So it's actually of this shape. Okay, and for both binary and K class, actually we are trying to maximize this shape here. Okay, so yeah, expounding this is a little bit time consuming, but just to get an intuition so that you know that the LDA, which is supervised, and they're doing something like this, and find the direction that will separate, separated points. I think that we have a diagram. Yeah, remember this okay, separate these 2 points. And that's probably sufficient unless you want to go deeper in machine learning. Yes, that's basically all of this slide. And usually we will, so the last thing maybe we can talk about, let me see what we have time. Yeah, so, if you have a one-dimensional matrix, take the outer product. The rank is also one, because this matrix generates just one vector. And so if you have different vectors summed together, at most there are k of them. So the matrix is at most have rank k. Okay, so usually, you will not have more than k, eigenvalues. Okay, so SB has a maximum rank k minus 1. Okay, because the summation, SB is a summation of k rank 1 matrices, and on freedom is k minus 1. Oh, if you know what I'm referring to. Okay, yeah. So that's all for this this course basically, right? So there's one question in written assignment. I think it's now pretty simple. It's just eigen decomposition for 2x2 matrix. Right? So I think in linear algebra, you should already know how to do that. If not, you can search the web. So, and these tools are in scikit-learn. Okay, you can easily call the libraries to use them. You don't need to do the calculation yourself. Right? So that's the whole purpose of this course, right? So understanding down there, it's not so simple. Right? Machine learning has some mathematics there. It's not just the called scikit-learn library. Okay, so and down the road, if you learn deep learning and also a lot of other things, and you know, this will help you also. Okay. So that's all for this course, and I will be here for QA for a while. And if you have a question, especially regarding the final project or assignment, please feel free to ask. Thank you. Again, I want to emphasize, so the final project due for the presentation next, you know, we have the 7 to 9 maybe, right? So we have the presentation time. Okay, just check the assignment description. Okay, for PhD student. Okay, otherwise you just need to submit and try to submit by Monday. If not possible, the latest Wednesday. Okay, after that we may not have time to mark all the assignment. Okay, so we have to have a time. Okay, thank you. And yeah, I also know that it will be super busy because you are not just taking this course. So yeah, so I will let you go unless you have questions. Okay, thank you.
We didn't take today attendance, Dr. Yan?
The last class I'm not taking attendance.
Oh,
Yeah.
okay. Thank you.
You're welcome. Bye. Yeah, you're welcome. Yeah, if you have a question, feel free to ask, especially this is the last week. Okay. And if you have any question, I think I may be busy tomorrow and Wednesday. I need to go out. And beyond that, maybe Thursday, Friday, if you really want to make appointment, ask a question, you can feel free to do so. Okay, you can make appointment with me by email. Thank you.
I have a question, sir.
Yeah.
Did you say we can submit the assignment by 9th?
Yeah, so we will allow you to be a little bit delayed by 9th. Potentially, we will not deduct the marks, but we really hope you can submit by Monday because we you know, everyone submit by 9th. We will need to work hard during the weekend, right? So, but no later than 9th, okay? Because after that, we will not have time to mark. Just imagine everyone is submit by Friday, then we won't have 2 days to go through. Right?
Okay.
Yeah, so the UAB has a requirement by the Monday after we have to submit all the grade, finalize them. Okay, that's why. Okay, I would be happy to have one more week, you know, but that's UAB rules. Okay.
Yeah. Other question I have, I don't know, you know, somebody asked earlier. We have one PhD student, right?
Yeah. So
we have 4 people.
Yeah, I already see the question. So now PhD students don't have to attend. Okay, you if you want to attend, it's a voluntary. PhD students have to attend because you need to present. Okay, at least the presenter, PhD student had to present for each week. Do I answer the question?
Yeah.
Yeah, that's good. Yeah, because we don't have time to go for all the students, right? So otherwise it will be too kind of consuming, right? We have so many students. Okay, everyone present. One class is not enough. Okay, so PhD students have to attend. Others are voluntary and welcome to attend.
Okay. Do they need to pre-book the time?
Yeah, so I actually put that in on the website for the final project. There's a description. If you look at the description down there, there's a time. I think it's 7 p.m.
Okay.
It's a final exam time.
About the report, what are you expecting in the report? The 3 requirement in slide number 3. If we answer those 3, will it be enough?
Which 3? I didn't.
Oh, in your final report slide, right? There are 3 requirements. The third one, introduce how you customize and fine-tune your model, right? That is one of them. Second one, report average precision metrics. Third one, show the best detection result.
So we will check these 3 parts, and if you they are there and you describe the method properly, we will give you the score. Right? So if not, we potentially will detect someone. Okay, so I understand this is a big, this is actually a big project, right? So if you just learn the machine learning, not deep learning yet, so we will consider difficulty also. So will not be unreasonable, but we do hope you can finish these tasks and show that you are able to train it. And because this is very important, because loss functions are basically classification and regression. Okay, so you have those concepts, and you will be able to go through some online tutorial, and you will be able to make something work. So that's all we need.
Okay. We are 4 people, so to get the full marks, do we need to do the image merging again?
Yeah, so
because
if you do the
image
merging,
right?
you will get 4 marks. If you don't do that, potentially you will get 95. We have to be fair to our students. If those students did an excellent job, right? So they get 4 marks, then you potentially will not get 4 marks. Okay.
Okay.
Yeah, but we will not be unreasonable. Give you an 8A or something. Okay, so that's what we are doing.
Okay. Thank you.
You're welcome. Okay, it seems that no one is asking more questions. So if that case, I will get offline, but feel free to email me. Okay, at least from Thursday, I will get more time. We can schedule some meetings if necessary. Thank you.